So welcome everyone to TCS Plus. Today we have Ola Svensson, and the operator for this talk is Oded Regev, and helping us out are Thomas Vidic, Thomas Hollenstein, Chi Kamat, and Clemma Canon. Now Oded will go around the table and introduce the groups.
Okay, thanks, Yonida. Thank you, Yonida. So today we have a group from Waterloo. Hello, headed by Amit Levy. Hello, everyone there. We have the group from MIT with Gautam Kamath. Hi, everyone. And we have the group from NYU with Shravas Rao. Hi, guys. Still setting up. And we have the group from Michigan State University, headed by Sorashai. And the group from Caltech with Thomas Vidic and others. Everyone. Okay, so back to you, Anidia.
Thanks, Oded. So, before we start the talk, a few reminders. So we have an exciting series of speakers lined up. 2 weeks from now, we have Charlie Kaufman. 4 weeks from now, we have Van Ras. And another 2 weeks from then, we have Stephen Fenner. So we have an exciting series of talks lined up. As is usual, you will be muted during the talk, but if you have a question, please unmute yourselves. Questions are very encouraged. Today we have Ola Svensson from EPFL. Ola, of course, has done a host of very exciting work in combinatorial optimization, including traveling salesman problems, scheduling, facility location problems, approximation algorithms, and very generally. He, of course, got the Fox Plus Paper Award for his work on approximating TSP. And today he's going to talk about how to use SDP hierarchies to do scheduling. So welcome, Ola.
Thank you very much. It's a pleasure to be here. Do you hear me? It's good.
Yeah.
Okay, very good. So please feel free to ask questions at any time. So I'm going to talk about the scheduling result, as mentioned, and this is based on joint work with Nikhil Bansal, who is in Eindhoven, and Arvind Srinivasan, who is at Maryland. So as I'm originally from Sweden, I like to motivate these scheduling problems by IKEA. So if you ever any time in your life bought a furniture for IKEA, you know, like it's very important to. Now it doesn't work. What happened? Okay. So it's very important to assemble the jobs in the right order, and also if you have done this, then different tasks take different amount of times and requires different qualifications. Okay, so this is to motivate scheduling problems where the processing time depends on which machine you assign it. Okay, so a job's process time doesn't only depend on the job, but also on which machine you assign it. So that's the unrelated machine model. Okay, so that's to motivate unrelated machines, but then you might not have the energy to solve that problem. So you go to Google and you search how to assemble or help assemble IKEA furniture. You search, then you have some patience for an algorithm working. Then you notice that there is a lot of ads, right? How to assemble furniture by IKEA. And as it turns out, you know, this is ads allocated by an algorithm to optimize some objective function. Okay, so maybe they optimize profit, fairness, social welfare, etc. But from an algorithmic perspective, these are basically very similar problems. And it turns out that it's a long-standing open problem to understand their approximability. For some of these objective functions, it's really weird, almost exotic situation that we can tell if there exists a good allocation, but our current best algorithms do not know how to find an allocation with the same guarantee. So I will mention this a little bit later. For some of the objective functions, we have better so-called estimation algorithms than our current best approximation algorithms. Okay, so that was a short motivation. So let's now define the scheduling problem, which will be the focus of this talk. So here we have input M machines. So in the example, I have 3 machines, M1, M2, and M3, and I have 4 jobs, so N jobs. Each job has a process time, Pij, that depends on the job and the machine. Okay. So in the example, I have simplified things for drawing. So here a job 1 has process time 1, but it can only be assigned to 2 machines. So you should think of this as the special case where job 1 has infinite processing time on machine M3. So you never would like to assign job 1 to M3. Okay, so this is a special case on unrelated machines called the restricted assignment problem. All right, so here in this example, job 1 has process time 1, job 2 has process time 1/2, 3 has process time 1, and job 4 has process time 1/2. So one schedule would be to assign 1 to 1, 2 and 4 to machine 2, job 3 to machine 3. And we want to, of course, evaluate our schedule according to some objective function. And one objective function that is popular is, of course, the makespan objective, which is the maximum load on a machine, or the time when we have completed all our jobs. Okay, so in this case, it would be 1. And then the second, I would guess, most classical objective function is the weighted completion time objective. So here, each job, in addition to its processing time, have a weight. Okay, so your makespan is 1. So every job has a weight. So here as an example, job 1 has process time 1 and weight 1. So here the weighted completion time of job 1 would be its completion time, which is 1, times its weight, which is 1. The second job has process time 1/2, so its completion time would be 1/2, and its weight is 2. So the weighted completion time of that job is 1. The fourth job has process time 1/2, so its completion time is 1/2 plus 1/2, which is 1, times its weight 1/2. So the weighted completion time of that job is 1/2. And then you sum up every time and you get your quality of service 3.5. Okay, so you think of the weight as the importance of the job. The higher weight, the more important the job is. Okay, so this is the problem we will mainly consider. So let's see what's known. And I usually make this joke to motivate the worst case analysis or approximation algorithms. So this is a car from the Lake of Geneva. So it's not often, but sometimes it gets fairly cold, and there's this humidity next to the lake. So if you go for dinner and you park next to the lake, you will find your car covered by ice. So that's like to motivate that this is an event you would never think about before you actually do it. So it's motivated worst case behavior. So now you're convinced that we would like to understand the approximability or approximation algorithms for these problems. And you cannot see, but the systematic study of the approximability started in the late 80s, early 90s, but the research on this problem started already in the 50s, as we will see later. And I think we have had very good success, in particular if all the machines are identical. So that means that the processing time is the same on all the machines. Okay, so this is a simpler case. And here the development of polynomial time approximation schemes gave a complete understanding, actually, with respect to these two objectives. So first there was in the 87 by Hoffman and Schmois makespan minimization on identical machines admit a polynomial time approximation scheme. And weighted completion time was a little bit more complicated. So that was first 99 that we gave, Guttella and Wogan gave a p-test for that case. And this is perfect because these results are tight because the problems are strongly complete. But unrelated machines turns out to be still mysterious. Okay, so current techniques fail to give a satisfying understanding, in my opinion, about unrelated machines. So to illustrate this point, let's look at the best current results. And the best current result for the makespan objective remains, the classical paper by Lasserre, Schmois, from 90s. So they proved that makespan minimization on unrelated machines has a 2 approximation, and moreover, it's NP-hard to do better than 1.5. And both the upper bound of 2 and the lower bound of 1.5 remains the best. So this, if you have read like Vatsirani's book, this is a textbook example of how to use extreme point structure in the design of rounding linear programs. Okay, so there has been some progress of special cases, and let me mention one in the restricted setting that I had in the example where Pij is in Pj and infinity, because here we have the weird situation that we have a 1.95 estimation algorithm. So that's an algorithm that in polynomial time estimates the optimal value of a schedule within a factor of 1.95, but it remains an open problem to design anything better when it's an approximation algorithm. Okay. So you see the difference. Estimation algorithm only approximates the optimal value. Approximation algorithm finds a solution within a factor of the optimum. Okay, so that's a really exotic situation. It's not many natural problems for which we have such a status.
Can you say a word on how come this happens?
Yeah, so you have a linear program, and the rounding algorithm that gives you 1.95 is not known to terminate in polynomial time. So it's a local search algorithm that we don't know how to analyze. It's running time in a good way, but it's guaranteed to return a good solution. That's why. Yeah.
This is similar to what happened recently with the rounding-based on the Srivastava speedrun, and is it similar, or there's just no algorithm, right?
Yes, there is no algorithm. Yes, here we have an algorithm to approximate the value. You mean for the Kelson-Singer?
Yeah, that MSS paper, right?
Yeah. Okay.
Singer. So I think
Yes.
they also have an algorithm to approximate the value, but they don't know how to find it because they don't know how to do the rounding efficiently.
Okay, then it's similar. Yeah.
Okay.
Probably for different reasons, but yes. Okay, so that's the situation for makespan, and for weighted completion time, it's not much better. So here, Hogevan give basically it's this APX hard, so you cannot get a p-test on unrelated machines. And the best algorithms was independent by Schultz-Custello gave a 3/2 plus epsilon approximation, and then shortly thereafter they removed the epsilon to get the 3/2 approximation. This was a 3/2 plus epsilon for any epsilon. So why does this happen? So the results on the top, they are based on a linear programming formulation which is called time indexed. So that such a linear program has pseudo polynomial size in the input. So if you have very large processing times, it will not be a polynomial size linear program. So to deal with that, they truncate the processing times. They round the process times within any accuracy, and therefore they get this 3/2 plus epsilon approximation. So the 3/2 approximation, on the other hand, they resorted to a convex quadratic program that I will a little bit mention later on and compare to our relaxation. But both results solve those relaxations, and then they resort to naive independent randomized rounding. So they solve the relaxation, and then they assign each job according to the fractional matching they get, independent of all other jobs. So it's a fairly naive rounding. So that's the state of the art here. So the questions you can ask is, can you do better than independent randomized rounding? And I suppose most people not coming from theory would say yes. Of course you should be able to do better than independent randomized rounding. You should be able to do something more clever. But you know, for many problems, in particular CSPs, this is the best you can do, like approximation resistance. So I guess in theory it makes sense to ask this question. And then a little bit philosophical question is, can we actually prove that weighted completion times is easier than makespan? So if we would improve the 1.5, then actually there is a difference theoretically between the two objectives. And as you might guess from the title, our result says yes. So we have this, before we had this gap between 1 plus epsilon and 3/2. Now we push this a little bit towards 1 plus epsilon. So we get the 3/2 minus c approximation algorithm. So now of course you wonder what so here's the theorem. Weighted completion times on unrelated machines has a 3/2 minus c approximation. You wonder what c is, so unfortunately so c is greater than 10 to the power of minus 7, so it's not a huge c, and we don't conjecture it to be tight, if I say it like that, so I think there is still jobs to be done. But I think the techniques are interesting, so we obtain this result by improving in two ways. So we formulate a new strong convex relaxation, which I think today, like 15 years later, would be the natural relaxation to get. Because now we are more familiar with this automatic lifting of relaxations. But previously, like the old 3/2 approximation used a little bit more magic way. And then we get a new rounding with strong negative correlation properties that I believe could be of independent interest. So in the
Yeah. So I have a question. So is it known like somehow like makespan that if you could have gotten a better approximation algorithm for makespan, that would translate to a 3/2 minus epsilon approximation for weighted completion? Like, is it known makespan is at least as hard as, approximating makespan is at least as hard in certain regime as weighted completion?
Yeah, good question. No. So if you have, for example, in many cases, weighted completion times would be harder than makespan. If you have precedence constraints, for example, then it's always the case that weighted completion time is harder than makespan because you can set a job at the end that has to finish after every other job. So we don't know of any such relation. Good question. Yeah, so in the remaining talk, I want to talk about how do we obtain our relaxation and how does it compare to the previous relaxation. This will then shed light on how do we need to improve the rounding, that I will explain in the second part. And they are fairly independent, so if you feel like things get out of hand, you can always relax to the next section. But I hope, just interrupt, I think it should be okay. Okay, so let's formulate a strong convex relaxation. And you can see that our problem is a little bit complicated because remember we want to minimize the weighted completion time. So it consists of two problems. The first problem is to decide on which machines should the jobs be assigned. Okay. The second problem is when I assign the jobs to machines, in which order should I execute the jobs on the machines? Okay. So first I need to assign the jobs to the machines, then I have to decide in which order to execute the jobs on the machines. Okay. So that turns out to be like that if I have to do both these decisions, maybe it's hard to write down a relaxation. But luckily, we can observe that it's really easy to schedule jobs optimally on a single machine. Okay, first observation, it's really an assignment problem. So the difficult decision is really about the first problem, on which machines should I, on which jobs should I assign to which machines. And so now let me explain how to optimally schedule the jobs on a single machine. So suppose we have assigned these two jobs to machine MI. And now I want to find out in which order should I execute them. And this is called Smith rule from 1956. So here I have a job. It requires one time unit on machine MI, and it has weight 2. And the second job requires 2 time units, and it has weight 10. So here you should think of this as a carrot. It has not so high weight, but it's fairly quick to produce. This is a diamond. It takes twice as long, but it has a much higher weight. Okay. So you can notice that, yeah. So let me take first, suppose I produce a carrot before the diamond. Now, what would my weighted completion time be? Okay. So this guy has weight 2. He will have completion time of 1. So it's 2 times 1 plus the weight of the diamond, which is 10 times its completion time, which is 3. So this would be 32. But you know, this is a bad idea because you can see that the diamond, he has more weight per unit time processed. He has 5 units of weight per unit time of processing time, whereas the carrot, they only have 2 units of weight per unit of process time. So the right way of doing this is like a knapsack, fractional knapsack argument, is to process the job with the highest weight per process time unit first. Okay, so I should process 2 before 1, and now if I do the calculations, I get the weighted completion time of 26. And this is exactly Smith rule. So jobs on machine I should be scheduled in non-increasing order of the weight per processing time unit. So you just take the weight over the process time on that machine. And yeah, the proof is just by substitution. Suppose this doesn't hold, swap 2 jobs and recalculate what the weighted completion time would be as the figure. So this is to say, like, once we have fixed the jobs, once we have assigned the jobs, it's an easy problem to do optimally. And we denote by this less than I, the Smith order machine I. So since it's unrelated machine setting, the order might depend on the machine because jobs have different processing times on different machines. For our algorithm, you could also assume that the weight depends on the machine, but let's stay simple. Okay. So now we have convinced ourselves that it's really an assignment problem. The problem is, how do we find a good assignment of the jobs to the machines? So now let's formulate a relaxation based on this intuition. So first I will formulate the exact quadratic program, and then we'll relax it. Okay. So since we know it's an assignment problem, we will have variable x sub ij that indicates whether job j is assigned to machine I. Okay. That's just that I want to say that every job should be assigned to some machine. So here I have, for every job, the sum over the machines xij is equal to 1. Each job should be assigned to one machine. And they should be 0, 1. Here I just wrote that they should be between 0 and 1. Okay. So this is just to say each job should be assigned to one machine. Think of this as indicator variables on which machine a job is assigned. But now I have to write the objective function. And I will write that as a sum of cost over all the machines, where the cost of a machine is equal to this complicated expression. So let's take a time to understand this complicated expression. So what's inside the parentheses? So the way you should parse this is that this would be the completion time of j if we assume that it's assigned to machine I. So let's assume job j is assigned to machine I. Then inside its completion time, it clearly has its own processing time. It has to have its own processing time in the completion time. But then it also has all the jobs that were assigned to the same machine that precedes it in the Smith order. Okay, so all the jobs that precedes it in the Smith order that were assigned to the same machine should be processed before it in an optimal schedule. So the completion time of j will be its own process time plus all other jobs assigned to the same machine that precedes it in the Smith order. So that's what this expression inside the parentheses says. So that would be the completion time of j if it was assigned to machine I. And if it was assigned to machine I, then we want to pay its weight times its completion time. Weight over j times cj. Okay, so that's the objective function. Any questions on that? That can be hard to parse the first time. Okay. So this is an exact non-convex quadratic program. Even if I relax these guys between 0 and 1. Why? So this can be seen like, suppose I could solve this program to optimality, then an independent randomized rounding would actually give an expectation exactly the value of the program. This can be seen. Just trust me. This is an exact formulation, of course.
Just to make sure the ordering on I is independent of the xij's. Is a fixed ordering based on your instance.
Yes. It's just based on the instance, yes.
And I'm going to use the fact that it's a function of wj over pij, or just an arbitrary ordering would also work?
Arbitrary ordering would also work.
Okay.
Oh.
Not sure what it means. Okay, so.
Yeah, so let's keep this order because I'm not sure that our algorithm would work. But the relaxation so far would work.
Right.
Okay, so just for the experts, the reason that an independent rounding would give you the same answer as the quadratic program is that you don't have a squared term of the same variable. So independent rounding would exactly satisfy the pairwise correlation. Okay, so that's our exact non-convex quadratic program. Now we want to relax it to something we can solve in polynomial time. And here I would say that the previous authors, at least today, does some magic trick. I mean, you would never believe this would work. Okay, so it is. I think it's kind of specific to this problem, but it's a very nice trick, and it turns out to work. So you start with some non-convex quadratic program, min x transpose dx. Okay, whatever you want. Now I want to convexify it. So what can I do? I just add some positive numbers on the diagonal, and if I choose lambda 1 to lambda n to be big enough, it will become convex, right? So now the question is, how much do I have to push up the diagonal, because that will affect my relaxation? And what I find quite magic is that in their papers, they show that for this problem we can select lambda in a smart way, so that if we solve the convex relaxation together with independent rounding, we get a 1.5 approximation. Okay. That's fairly magic to me. So that's the way they get their relaxation. They push up the diagonal to make sure that the matrix is positive semi-definite. Okay, but today, how would we do today? Today, probably most people would just do some lift and project. So how would you convexify this program? So we have a quadratic program that is non-convex. So the problem is really this non-linear terms, right? You have x sub ij times x sub ij prime. We want to linearize these quadratic terms. And I suppose the easiest way to linearize them is just to replace this product by a new variable, y sub ij prime. Okay, and now you get a new variable. So now you have a linear program, and you just want to add constraints so as to try to enforce some consistency between the new variables. Ideally, they should correspond to the product, right? And the way you do it in these hierarchies is to add valid constraints on these variables. In particular, in Lasserre and sum of squares, you would add some kind of positive semi-definite constraints. Okay. So if you have never seen that, it's impossible to understand. So let me just say that you add constraints so as to ensure that there is a distribution of assignments that basically agree with the pairwise correlations that your relaxation gives you. So you want that there exists a distribution so that the probability that j and j prime are assigned to I is roughly equal to the variable you have up here that should be equal to that probability of correlation. Okay. And this is similar to like in the max cut algorithm, right? We have here we have also pairwise correlations, and we use STPs to give us these pairwise correlations that will later on approximate this moment by a binary distribution. Okay, so with this intuition, let me write our relaxation. Okay. So again, we have the variables x, that is a fractional assignment of the jobs to the machines. So the only thing we will change is how we define this cost I, which is the cost of machine I in expectation for this fractional assignment. Okay. So now the cost of I will equal the minimum cost of machine I over all distribution of assignments satisfying the marginals given by x. Okay, so let's look at an example. So here I have machine I have two jobs, okay? Both have process time 1 and weight 1, okay? And in the fractional assignment x, both are assigned with 0.5 to the machine mi. So 1 is assigned to mi with 0.5, 2 is assigned to mi with 0.5. So now we look at only on this machine, what's the integral assignments over jobs satisfying these marginals that minimizes the contribution of this machine. So one distribution satisfying these marginals would be, hey, we probably do 0.5 assign both jobs to mi. Okay, so that would then schedule 1 and 2. That would have expected cost 0.5 times the cost of this assignment, which would be 1 plus 2 in this case. So 1.5. A smarter distribution would be assign jobs disjoint with equal probability. So with 0.5, assign 1, and with other remaining probability, assign 2 to that machine. Okay. So now in each case, you would pay. Here, the cost of the machine would be 1. I have one job with process time 1 and weight 1. And here I have another outcome where I again have a cost of 1. Okay, so here the expected cost of that machine would be 1. Okay. And what I say is that our relaxation will say that the cost of this machine is the minimum such cost over all such distributions. And in this case, this turns out to be the best distribution to assign them disjointly. Okay. So mathematically, I could write the cost to be that expression. So I minimize of all the distributions, satisfying the marginals, and here I just have the cost of that machine. Here I mean distributions that are assignments to that machine. So notice that this is not, it doesn't solve a problem, because for different machines we have different distributions and they might not be globally consistent. Okay, so for a single machine you get the distribution of assignments satisfying the marginals, but they are not globally consistent. So now the question is, how do you take these local distributions and turn them into global distributions?
Well, just to make sure, so
Yeah.
are you actually using Lasserre? It seems like you're only using the Shirley Adams. You're only using linear programming at the second level. Does it make sense?
So to my knowledge, we need a PSD constraint later on. Yeah. So to my knowledge, we use Lasserre. So we don't need the full power of Lasserre. We only need the Lasserre constraint machine by machine. So we only need a PSD constraint by looking at a single machine. So we don't need to add the whole moment matrix. Okay, so what's important is to look at a single machine and then add the constraints there. And that we also do in the papers. We don't have the full power of Lasserre. We have actually a smaller program than Lasserre.
Okay, but you're going to you haven't used it yet, I think. The PSD does.
Yes. Okay. Yes. Very good. Too good. And then I should also say that the PSD constraints do not imply this full power, that they have an integral distribution for a single machine. But a result by Svidenko and Wiese actually gives us such a power for this problem. So they show that the linear program called Configuration can be solved for this problem. And then you have an integral distribution for each machine. So that's another relaxation that is way more complicated than the one we are doing. So it's you need to use ellipsoid to solve it, but it might give you additional strength. Okay. But that's a detail. Let's think about this as a relaxation. We can think of this as a relaxation without loss of generality. And I will point out where we use the PSD constraint. Any more questions on this? Okay. So let's understand.
Sorry. Yeah, I just have a quick question. So this minimum over mu, can you speak, how is that computed? Is it obvious that you can?
Yeah, it's a good question. So in the relaxation, it would imply that then the relaxation gives you mu for each machine.
Sorry, can you say it again? Who's the idiot that muted him?
Oh, can you repeat the answer once more?
You were muted for some reason.
Well, accidentally, I think I muted you, so you have to unmute yourself. If you go to the Hangout, try to unmute.
Okay, now you can hear me.
Yes.
Okay, so I rehearsed 3 times the reply, so maybe it makes sense this time. So in the relaxation that implies this, the relaxation actually gives you the distribution for each machine. It's something called a configuration LP. So then you can just read the relax. So here I try to simplify by just saying that our cost I is equal to the minimum, but actually the cost I is equal to the value for the distribution that the relaxation gives you. Okay. But it's a different distribution for each machine. It's called yeah. So there you don't need to calculate the distribution afterwards. Yeah, but you can do it. Yes. Good question. Okay, so let's understand why this relaxation is stronger than previous relaxations. And here we will use the PSD constraint. So understanding the relaxation. And let's be simple. So consider a single machine I, and we assume for simplicity that on this machine, all the process time of all jobs equal their weight. Okay. The reason I assume this is that then the Smith order, any ordering of the jobs are equally good, right? Because all the jobs have the same Smith order. And then I can simplify the expression of the cost to this expression. Okay. You notice the only thing, don't read the expression exactly, just notice that the dependency on the Smith order disappeared. And this is just because the Smith order doesn't matter anymore. All the guys have the same process time and the weight. All the guys have the process time equal to their weight. All right. So now we have that expression. Don't worry about it. Now I move in the expectation just by linearity of excitation. Okay. And now see that you have this quadratic term. The blue term is the expectation of something quadratic. Right? This is sum of indicator variable. If that job is assigned to machine I, its weight. So it's basically the sum of weights assigned to you squared. The expectation over that. Okay. And now you can use Jensen's inequality to say that this at most, I can move in the expectation in the square. Okay. And this turns out to be previous relaxation, and the one before was our relaxation. And here we use the PSD constraint to go to somehow, because with the PSD constraint we don't really have a distribution, but we want somehow our relaxation to give us this additional power for this quadratic thing. So you see that these two expressions, our relaxation and previous relaxation, are exactly the same except for the blue and the red part. So the only difference is the blue and the red. We have not moved in the expectation yet. So in particular, if the blue part is much bigger than the red part, then we are already better. Because then we have a stronger relaxation, and we knew that the independent rounding does a 1.5. So then independent rounding with respect to our relaxation does better than 1.5. So whenever the blue expression is bigger than the red expression, we are doing better than 1.5. I just copy the blue expression from our relaxation and the red expression.
I have a question. So I thought independent rounding, the reason independent rounding was working was that there were no like x squared terms.
Yeah, that's why you lose the 1.5. Like once you have pushed up the diagonal in your matrix, you get these terms.
So what I'm asking is, even if the relaxation, the current relaxation you have is better than the previous relaxation, is it obvious that the rounding will strictly do better on the current relaxation than the previous one, or is it something that can be proven but not necessarily true?
I mean, if you have two relaxations, one returns a value that is bigger than the other one, and you know, so you have like two values, one is bigger than the other one, and you know that your rounding will be 1.5 times the low one.
Okay. Got it. Sorry. I was being
no, it's good. So what all I'm saying here is, if our relaxation significant, there is some epsilon flying around here, but if our relaxation significantly beats the previous relaxation, we're all happy. And this happens if this blue part is bigger than the red part. So if Jensen's inequality is not exactly tight, for our instance. All right, so let me just move the red part to the left. Okay, so then I have greater than 0. Can you see what this is? Now we have expectation and So if I would say that this is y, that here, and this is y, so then I have the expectation of y squared minus the expectation, so the squared outside of the expectation. So this is exactly the variance of that expression. So whenever the variance of the amount of weight of jobs you assign to the machine is bigger than 0, our relaxation is better than the previous relaxation.
Just to clarify, it's variance
Yeah.
over the distribution over the
Yes.
samples, right?
Yes.
We should somehow get familiar SDP
Yes.
Lasserre.
Yes. Exactly. This is very abstract, so let's look at an example. Yes, the variance of total weight of jobs assigned to I over that distribution we get from the relaxation. So let's do, when is our relaxation better? Let's do it 2 cases. Case 1, we have 3 identical jobs. So here I use 1 to denote the process time and the weight of the job. So 3 jobs of process time 1 and weight 1, each assigned with fractional probability 1/3 to machine MI. In case 2, I have a job of process time and weight 1, a job of process time and weight 2, a job on process time and weight 3. Again, each one assigned with probability 1/3 to our machine. Okay. So here, the optimal distribution of assigning these jobs is again to assign them disjointly. Okay. So you assign this job by itself with probability 1/3, this job by itself with 1/3, this job with probability 1/3. So in any outcome here, the weight you assign to this machine is 1. Okay, so the variance is 0. Okay. Here again, in the second example, it's the same thing. The best distribution you can have is to assign this guy with probability 1/3, this guy with probability 1/3, and this guy with probability 1/3. But now they have different weights and different sizes, right? So the variance will not be 0. Okay. So if you make the calculations, our relaxation would have the blue expression equal to 1 in the first case. The previous relaxation would have equal to 1. That's a bad case. We don't know how to do, right? Because our relaxation has the same value as the previous relaxation, so we didn't gain anything from previous works. In this case, if you do the calculation because of the variance, our relaxation will have value 4.67, previous relaxation will have value 4. This is intuitive, right? When you have fractional assignment of very different jobs, there is no way to even them out to have variance very small. That's a good case. So that's us how technical I wanted to be about the relaxation. So if you have no questions, let me just summarize the main points. And now if I lost someone, they can happily come back. Okay. So main points about relaxation. We can obtain it an automatic way from exact quadratic program. We don't need to do this magic trick, as I call it. And it's fairly small. It's just a square, nm squared. And it gives a better bound for machines that are fractional assigned of different types of jobs. So for those kind of situations, we're already better than 1.5. Okay. So what we really have to worry about now is fractional solutions where a machine has basically jobs of the same type assigned to it. Okay. Because otherwise we already do better than 1.5. So that's the point. We have to worry about these instances. So if you that's what I'm going to spend the remaining part on. So how are we going to do on this instances where we have an assignment of jobs that look the same? Because the other jobs we already do better on. So let's convince ourselves that we need to do some extra work, because otherwise we might already be done, right? Maybe independent rounding does better than 1.5 on these particular instances. So let's look at independent rounding that I talked about the whole presentation. So it source the relaxation to obtain x. Then for each job j, assign it to machine I with probability x sub ij, independently of all the other jobs. So here in an example, I have 2 identical jobs, the problem we are considering, and each job is assigned with equal probability to the 2 machines. So here the optimum solution is that each job is assigned to different machines. So job 1 is assigned to machine 1, job 2 is assigned to machine 2, and this will have optimal value 2. What is the independent randomized rounding? Well, let's look at the cost of machine 1 in expectation. So with probability 1/2, it will get 1 job. that has a cost of 1. We probability 1/4 it get both jobs, and that will give cost 3. So the cost of this guy is 1/2 plus 3/4. And now you have 2 of these machines, so the expected cost would be 2 times 1/2 plus 3/4, which is 2.5. That's not too bad. We have a 2.5 versus 2. That's a good approximation. But let's replace 2 by n. Okay, and now you get that opt is equal to n, and the relaxation is equal to n. So the relaxation has the perfect value, right? But the independent rounding gives 3/2. So it's really that the analysis of 3/2 for independent rounding is tight. So we need to do better rounding for these instances. And now this is where negative correlation comes into play, because we want negative correlation in the following sense. If I assign a job to machine I want to make it less likely to assign other jobs to that machine. Because it's a bad case when many jobs becomes assigned to the same machine, right? So I want to get negative correlation between the assignment of jobs. If I assign a job to machine I want to make it less likely to assign other jobs to that machine. So that's what we're going to do. So let's just make the point clear. Independent rounding is no better than 1.5. You can make more complex examples to rule out simple modifications. We need to improve independent rounding for jobs of similar type.
The 3/2 system calculation didn't show us, right? Something with the Poisson distribution.
Yes, exactly. Yes. Yes, so we need to do better. So let's see what we do. So here I have the example. I have k jobs with process time weight equal to 1. I have k jobs with process time weight equal to 3. Let's see the guarantee of independent rounding of these jobs. So here I think of each job to be assigned to machine I with probability 1/k. Okay, that's the fractional assignment here. So independent rounding has the nice property that it satisfies the first moment. So the probability that j is assigned to I is exactly equal to xij from the relaxation. It's defined in that way. And the probability that both j and j prime are assigned to I is the product of the fractional variables from relaxation. So for example, the probability that I will assign this job to I and that job to I is exactly 1/k squared. Okay? Now we want to beat this, but we never want to do worse than independent rounding. So what we do? First, we partition jobs into groups on a machine. Here I make an example. I have 2 groups, the blue group and the red group. The only thing they need to satisfy is that the fractional assignment sums up to at most 1. So the sum of fractional assignment of the blue jobs is at most 1. The sum of fractional assignment of the red jobs is at most 1. Okay. And now let me state the guarantee of our rounding. So first we satisfy the marginals. So probability j is assigned to I is equal to xij, as in independent rounding. And then we never do worse than independent rounding. So probability j and j prime are assigned to I is at most the product. But if they're in the same group, we do better. So then we have 0.99 times the inner product. So we have a stronger negative correlation between jobs that happen to be in the same group. And that's where we win, because this makes it less likely to assign 2 jobs to the same machine or many jobs to the same machine of the same type. So let me note here that this statement holds for any grouping. In our application, we group similar jobs of the same process time and weight. Okay, but the statement holds for any problem of such bipartite assignment type. So it looks like you should have any problem where you use independent randomized rounding of this type. You would like to apply this technique maybe, because this should allow you to give some additional mileage when you have this 0.99. Hopefully also you could replace 0.99 by something better. Okay, but even here you get better than independent rounding, and you're sure to not lose anything because you do as good as independent rounding for everything. Okay. So it's the combination of this new relaxation and this rounding that gives us the improvement. So let me quickly then let me explain how you can obtain such a result. So we want a strong negative correlation between the jobs in the same group. Okay. So the groups I identify with these small green squares here. Okay.
I'm missing something. Why can't you just choose one of them? I mean, you have
Yeah.
Okay, sorry.
Good. Yes. So that's my first trial. So now Oddet's suggestion is, why can't I just choose one? Let's think of the small green boxes as a bitype matching instance, because I had this constraint that the sum of fractional value coming into them is at most 1. So think of this as a half integral solution. So this means that each job here has a fractional value of 1/2 on each edge. Okay. So now Oddet's suggestion is, it's a good one. It's the first natural one. So that is to just find a perfect matching, or a matching of the jobs, so that you have at most one guy in each group. Okay. So you think of this as a bitype matching problem. So the way to do that, I suppose, is to do something called pipage and swap rounding. And the way that works is that we first select an alternating path cycle in the support. So we start with this blue edge. Then we get the green edge, blue edge, green edge, blue edge, green edge, blue edge, green edge, until we close the cycle. Now you randomly either increase the blue matching and decrease the green matching, or you do the opposite, decrease the blue matching and increase the green matching. Okay. So this would be a way to round these kind of bitype matching relaxations. Oh, someone lost my video.
But here everything is okay.
Okay, so as long as Odded see. Yeah. Okay, so now we have this alternating cycle. Okay, so now we either increase the blue ones, decrease the green ones, or the opposite with equal probability. So now this would mean that you either get the blue assignment, and as Odded said, this gives me one job in each group. It's perfect negative correlation. Or I get the green guy, and again, it's perfect negative correlation. So what's the problem? Why don't we just use this? Because you also get perfect positive correlation between jobs being assigned to the same machine. So for example, in this case here, I have these two jobs, these two blue jobs, they're always assigned to M1, the machine, at the same time. So here, you see that these guys, in this rounding, I would always assign them to the same machine at the same time. So the probability that these two jobs will be assigned to M1 is 1/2 instead of 1/4 as you would have gotten in the independent rounding. So we get perfect correlation between jobs in the same group, but between jobs of different group, we might get perfect positive correlation. And that's a problem because we never want to do worse than independent rounding. So the rounding has perfect negative correlation for jobs in the same group. However, some jobs have perfect positive correlation. And we never wanted to do worse than independent rounding for any pair of jobs. And why did we get perfect positive correlation? Well, let's look at how we built up our update procedure. And the problem was here. We have a path of length 5. Now we have two blue edges going to the same machine. And they are perfectly positively correlated. Either I increase both or I decrease both. So for those two assignments, I'm doomed to do worse than independent rounding. Is that clear? Okay. So I will do perfect negative correlation inside the groups, but between groups on the same machine, I get perfect. I might get positive correlation. This is don't want. So here you see that paths of length 5 may go back to the same machine with perfect positive correlation. So length 5. So what do? Well, in our rounding, we restrict ourselves to length 4 paths, and then we don't get into this problem. Okay, so that's our rounding. Okay, so let me just move my image. All right. So solve relaxation to obtain X. Do grouping. Now each job selects a random edge and colors it red. Okay, so here this job selected this edge and color it red. That job selected that edge and color it red. This, that edge, and so on. What's the intuition? The intuition is that we will maintain the following invariant, that at most one red edge in each group will be assigned simultaneously. We will forget about the edges colored black. Those we will allow to be assigned to the same group simultaneously. And the reason is that if we don't do something like that, then we get these long paths which will have a horrible correlation, positive correlation. So we want to break it into we want to less negative correlation in the groups, and the way we do it is to color them randomly in red and black. We will only obtain a negative correlation on the red guys in the same group. Okay, so that's the first part. Each job selects a random edge and colors it red. Now, while there exists a path beginning in a black edge, then a red edge, black edge, we do a pipage rounding. Okay, so either we do plus, minus, or the opposite with equal probability. Okay, so notice that this has perfect negative correlation still on the red edges in the same group, because it's plus minus, and also in this case the black edges turn out to go to the same machine M2, but they also have perfect negative correlation. So I will never change two jobs to the same machine so that they have positive correlation in this way. Okay, so maybe I selected that. And then once I don't have this black, red, black path, I do independent rounding. And that's my rounding. Yeah, I could have done that as well. So let's look at a bigger example. I select my red edges. I have a black, red, black path. I select one of the two paths at random. Increase, decrease. Get that assignment. Select a new black, red, black path. And I select one of the random, and I do that until I don't have any black, red, black path anymore, and I do independent rounding. So this is the end of the algorithm. So that's the whole algorithm. So notice that when I finish, I don't have any group with two red edges incident to it. So in particular, if two jobs were in the same group and both those edges were colored red, then they will not be simultaneously assigned to that machine. So this is where we get this additional negative correlation. So analysis. This is it will be it's not much complicated left. So first, we still have that we assign with marginals that probability j is assigned to I is equal to xij. This is just because we increase and decrease with equal probability. This is like each job is increased and decreased with equal probability. So intuitively, you should not have the same probability of being assigned as the relaxation told you. Okay. Probability j and j prime are assigned to I is at most xij times xij prime. So we are never worse than independent rounding. And this is because we have this path of length 4. So the updates are always negatively correlated on a single machine. You see, either I take plus minus or plus minus. I take plus minus or minus plus. So it's always different signs. So they are negatively correlated. Why do we better if they're in the same group? Well, in the event that both these edges are colored red, we will never assign them to the same machine. And if they are not both colored red, we do as good as independent rounding. So if ji and j prime I are both colored red, which in this example would happen with probability 1/4, then we have perfect negative correlation. Otherwise, at least as good as independent. So in this example, we would have gotten 0.75 times xij times xij prime. But in more general cases, you don't get that good. Okay. Okay, so that was our guarantee, and that ended the technical discussion. So to recap, to improve the 1.5, what we did was to get this new relaxation that allowed us to deal with the variance on a machine was high. And then we got this new negative correlation rounding that dealt with the case when I grouped jobs of similar type. So I gain when they're different, I gain when they're the same, and I gain 10 to something in the approximation guarantee. So let's finish with some open problems to just convince you that there's a lot to do. So one question is related to Oda's question. Why am I so obsessed with never doing worse than independent rounding? Maybe the pipage rounding is a good rounding if I manage to group the jobs in a smart way. It's just that we are not able to analyze this. So now it's easy to analyze because we know that we never do worse than an independent rounding that is guaranteed to do 1.5, and we gain a little bit. But maybe positive correlations are not so bad if you're able to group, you have perfect negative correlation between similar type jobs. We don't know, but this seems like a reasonable thing that you should not be so obsessed about always doing better than independent rounding. Then I would admit that the guarantees are probably not tight here. So there's still to be done, and this holds for all problems. So as I said, make span, this Lasserre moistage from the 90s is still the best, 2 and 1.5. Restricted mean make span, it's this weird situation where we could do better estimation and approximation. Max mean, the guarantee is non-constant, the hardness is 1/2. That's more like add allocation or fairness. Restricted max mean is 1/4 versus 1/2. And both these restricted mean max, restricted max mean is this really weird situation where current best approximation algorithms are worse than the current best estimation algorithms. It's because of the same reasons. Yeah, so need improved methods. Basically, we don't have good enough methods to analyze these strong convex relaxations for allocation problems. The roundings are not clean and tight. Thank you. I don't know how the animation works in the Google.
Thanks. Thanks, Ola. Do we have any questions?
No question.
No, I mean, so one thing is like the last rounding part. So you're trying, I was just trying to understand, like the last rounding part was a question about that you have some pairwise correlation constraints and some single marginal constraints, and you want to come up with a probability distribution.
Yeah.
I'm trying to understand, like, is there a clean probabilistic fact one can take out of that, the rounding algorithm, because it didn't seem to have much to do with the scheduling problem, more like
good.
A bunch of.
Yeah, I tried to make that point. Very good. Thanks for asking. So this is completely independent from the scheduling problem. This holds for any such problem, and you can group the jobs or the items or whatever you have as you want, as long as the sum of incoming fractional values at most 1. So yes, this result is completely independent from scheduling. The way we apply it in the scheduling framework is to group similar jobs. Another note is, I could say, is that I talked about that we get the distribution from the relaxation per machine. This distribution we completely throw away after we have argued that we are in this case. So somehow we only look at the marginal probabilities of the relaxation. I don't know if one can do something smart by looking at the second moments.
So the way this works is, so the entire algorithm, the entire thing, not just the rounding, the way this is working is either you're saying either the variance is bounded away from 0, or if the variance is super close to 0, then this rounding algorithm will do a little better than independent rounding. So
yes, but we always run our algorithm because it's always as good as independent rounding. We can only gain by running our algorithm.
okay.
But then we show that if we don't gain a lot, then there must be high variance.
Okay.
Very good.
Do we have any more questions?
So no questions. Let me go offline, but everyone is welcome to stay here and chat longer. Okay. Or do you want to announce the future talks, Anidia?
Oh yeah, sorry. So yeah, so the next talk is by Charlie Kaufman. That's 2 weeks from now, and after that we have Anwas and then Stephen Penner. So we'll see you 2 weeks from now during Charlie's talk. Thank you.
Okay, thank you, Ola.